So good morning, good afternoon, good evening, wherever you are. It's my pleasure today to introduce Associate Professor Jessica Kasza from Monash University. We'll speak about stepping up and crossing over design efficient cluster randomized trials. Jessica is Associate Professor in Biostatistics in the School of Public Health and Preventative Medicine at Monash University, completed a PhD from the University of Adelaide in 2010, spent a bit time in Copenhagen, moved back to Adelaide, and then since 2013 is at Monash University. She's currently president of the Statistical Society of Australia, and we're very pleased to have her here as the Matrix seminar speaker. Jessica.
Thanks, Jan. I'll share my screen and get started. Can I just get a thumbs up, Jan, that you can see that okay?
Yeah, all good, Jessica.
Thanks very much. Just like to confirm that before I launch into things. Yeah, so today I'm going to be talking about some of the work that I've done with a variety of colleagues, excuse me, on designing efficient cluster randomized trials. So the work that I'm going to be talking about is work that's been done in collaboration with people from the Costa Cluster at Monash. The Costa Cluster at Monash is a group of people who are in the Biostats unit in the School of Public Health at Monash. We work on various aspects of cluster randomized trials. We've got Stefan and Andrew, both professors, myself, of course, Reese and Kelsey are postdocs with us. Ehsan has just started his PhD with Andrew, Kelsey and myself. And Lizzie is another PhD student who her PhD is actually in a different area, but we're lucky enough to be working with her on a few aspects of cluster randomized trials. So it's a really great group. And a lot of what I'm talking about has been done in collaboration with one or more of these fantastic people. All right, so let's get started. I do want to start out at a relatively low level, just to make sure we're all using the same terminology, the same words for things, the same notation. Not that I've got a whole lot of notation in this talk. I think most people have a fairly good understanding of what a randomized controlled trial is, randomized clinical trial. So you might conduct a trial like this when you want to assess whether some new treatment, some new intervention works better than the standard or than some control. So people are quite familiar with placebo-controlled trials. So in these settings, we would have individuals come into our trial. Some of them would be randomized, half of them would be randomized to receive the active treatment, and the other half would be randomized to receive the placebo, the control condition. So randomization is fantastic because it implies that we can expect our control and intervention groups to be similar. So any differences that we do end up observing in the outcomes for our participants between these two groups, we can say that that's due to the differences in the treatments that they received. So individual randomization is often referred to as the gold standard for assessing the impact of interventions. But individual randomization isn't always possible. Sometimes our interventions are instead applied at the group level. So one example of this is a hospital cleaning program. So there was a trial conducted a few years ago in Australia where a new program for cleaning the wards within hospitals was being tested against the standard. So the idea was that this new cleaning program would reduce the number of hospital-acquired infections among patients. So the treatment, this new cleaning program, was applied at the hospital level, but our outcomes were measured at the individual level. So we measured whether each patient within the hospital got a hospital-acquired infection. So in this setting, we can't randomize the patients to the treatments. Patients go to the hospital that's the best one for them. It might be the most convenient hospital for them. It might be the one that can treat them appropriately. But we can't randomize patients to these treatments in this setting. Instead, we need to randomize entire clusters. So in this example, we would need to randomize entire hospitals to either implement their standard cleaning program or this new upgraded cleaning program. So we would be randomizing clusters of individuals rather than the individuals themselves. And hopefully you would have far in excess of the 4 clusters that I've shown here. So when we're thinking about interventions that are applied at a group level, we can't randomize individuals. We instead randomize our clusters, our groups of participants. So these clusters could be hospitals, already mentioned an example there. They could be intensive care units. They could be schools, neighborhoods, families, any grouping of people. The problem with this grouping is that we no longer have complete independence of observations. So if you've got a bunch of people who are being treated at the same hospital, in the same environment, are receiving similar care, perhaps being treated by the same clinicians, then we no longer expect their outcomes to be completely independent of one another. They may be interacting with each other within this cluster, if you consider family groupings, for example, a lot of interaction going on there. So the point is that when we do this cluster randomization, we no longer have complete independence of our observations. And the intra-cluster correlation, which I may refer to as the ICC as we go, and I'll use the Greek letter rho to denote this, describes the similarity of outcomes from participants who are in the same cluster. This ICC can vary between 0 and 1. It lies between 0 and 1. If it's equal to 0, it means we've got complete independence of our observations. We may as well be running an individually randomized trial. Well, we are essentially running an individually randomized trial. If it's equal to 1, that means we've got complete dependence between our observations. So even though we might collect a whole bunch of data from a cluster on a whole bunch of participants, it's as though we've only collected one piece of data. So the ICC is between 0 and 1. The greater this ICC, the greater this similarity, the more participants we're going to need to get the same amount of information about the intervention effect as we would have needed if we did an individually randomized trial. So we're going to need in excess of the number of participants as we would if we'd done an individually randomized trial. This dependence means we need to get more data to get the same level of information. So we often expect these ICCs to be relatively small. So in some work that Lizzie led, in fact, we looked at ranges of ICCs for a range of different cluster randomized trials and clustered data sets. And we found that often these are relatively small. It's not unusual to see ICCs of around 0.01 or 0.05. So these are small values, but even small ICCs can lead to a large number of required clusters. So often when we're designing these cluster randomized trials, we'll calculate this quantity known as a design effect. So if we've got clusters of size M, so M patients or participants within each cluster, we would calculate this number, so 1 plus rho times M minus 1. And then we would multiply the number of participants we would require from an individually randomized trial by this design effect to get the number we need to account for this clustering we have, to account for this ICC. So if we've got clusters of size 100, we've got an ICC of 0.01, our design effect is going to be almost 2. So we need to double the number of participants we require. In practice, many of the clusters we're dealing with are going to be even larger than this. So you can see that for large clusters, even small ICCs can have a huge impact on inflating your required sample size. So this talk isn't about the impact of ICCs on outcomes, but I did just want to mention this. And I also wanted to say that when you do have this inflation of participants being required, you could think that just adding more participants within each cluster might be a good idea, but there are diminishing returns when you include these extra participants. At some point, you will need to add additional clusters to your study. So this means that cluster randomized trials aren't always feasible, even though they may be, well, seemingly the only choice for assessing our intervention. What if more clusters are required than are available? So a good example where this happens when planning these studies is in the intensive care unit setting. So in Australia, we've got about 35 to 40 ICUs that participate in research. If we want to conduct a cluster randomized trial, even though we might have a really small ICC around 0.01, it will often turn out that we need more than 40 ICUs to actually detect the effect that we're interested in, the effect that is clinically meaningful. So what can we do in that setting? What can we do if we do our sample size calculation and we find that more clusters are required than we actually have available? Well, one thing we can do is extend our cluster randomized trials over time. So longitudinal cluster randomized trials are super helpful here. So with these longitudinal cluster randomized trials, clusters are followed over time and measured repeatedly. So you've got your group of participants and you've got your cluster, and each period of the study, you'll go into that cluster and take measurements. So you may have the same participants within each cluster being measured multiple times, or they may just contribute once. They pop up in one period, they're never seen again. In the next period of the study, you get a whole bunch more participants. The point with this longitudinal term is that the clusters are followed over time. The clusters can also switch between control and intervention conditions in these longitudinal cluster randomized trials. And this is really useful. This switching between control and intervention conditions means that we can make comparisons not only between our clusters, but within our clusters as well. And it's this within cluster comparisons that we can make that lead to these increases in power and that turn an infeasible study into one that is actually quite feasible and possible. So a really good example of a study that does this really well is the cluster randomized crossover trial. So in the cluster randomized crossover trial, instead of randomizing our clusters to the control and the intervention condition, we randomize our clusters to implement a sequence of interventions. So clusters randomized to sequence 1 in this study would be implementing treatment A for the first period of the design, and then cross over to treatment B in the second period, while those randomized to sequence 2 would go the other way. They'd start off with treatment B and end up with treatment A. So this is really a useful thing to do because we can now compare between the treatments A and B between our clusters, but we can also make these within cluster comparisons. We can look at what's going on within a cluster when we change our treatments. This is actually the most efficient design you can have. So if you can conduct a cluster randomized crossover trial, then I would encourage you to do so. However, there are many practical reasons why the cluster randomized trial might not be able to be used in your setting. So here we need to switch back and forth between treatments. We need to go from treatment A to treatment B and from treatment B to treatment A. But this switching back and forth isn't always possible. And this will often depend on the sort of intervention that you're considering. So one other cluster randomized trial example that has been conducted in Australia in recent years is a GP training program where GPs, general practitioners, are trained in treating patients with knee osteoarthritis. So patients with knee osteoarthritis would go to their GP, and if that GP clinic had been randomized to the intervention, then hopefully their GP would have all of these additional resources available to them to help them treat that patient. In the other arm of the trial, the GP clinics would just do what they usually do. So in this setting, we're educating our GPs, we're training our GPs. It's really difficult to untrain someone. It's really difficult to uneducate someone. Once you've told someone about some new resources, taking that away from them can be very difficult. So we often find with these education-based interventions that switching back and forth isn't possible. Another situation in which a cluster randomized crossover trial might not be possible is if we're considering a change that's going to be rolled out across our clusters anyway. So there might be some new bit of machinery that's being implemented across a system. A new way of doing things is going to be implemented across a system. Some new policy change has been, will be implemented. So in this setting, we know that all of our clusters are going to eventually be implementing this new intervention. So we can't do this switching back and forth in that situation either. So when the cluster randomized crossover trial can't be used, a design that you could consider is the stepped wedge cluster randomized trial design. So I think stepped wedge designs are pretty wonderful. I think that they are fascinating from a statistical point of view. I've spent a lot of time thinking about stepped wedge trials over the past few years, and we've had some interesting insights. Well, I think they're interesting anyway. We'll see what you think as we go. So this is an example of a stepped wedge design. So this is a 3-sequence design with 4 periods. In this design, clusters would be randomized to one of these 3 sequences. So clusters randomized to the first sequence would start out implementing the control condition before switching over at the start of the second period to the intervention and remaining on that for the rest of the design. Clusters randomized to sequence 3 would stay implementing the control condition for 3 periods before switching over at the final period. So this is one example of a stepped wedge design. You can have a greater number of sequences, you can have a greater number of periods. The point is that all of the clusters start out implementing the control, and over time will start implementing the intervention. And in the final period of the design, all of the clusters are implementing this intervention. So this design is really useful in situations where we can't switch back and forth, when once a change has been implemented, it can't be undone, or it's more difficult to undo. It also could be useful because all of the clusters know they're going to receive this intervention eventually. And that might help to entice clusters to participate in your research project. It's also useful when interventions can't be undone or are going to be rolled out anyway. So the stepped wedge design is pretty interesting, but it places a large burden on the participating clusters. Clusters need to be involved for the entire duration of the trial. They need to contribute data, measure their participants, their patients, the people at that cluster in each period of the design for a potentially long period of time. So something that my colleagues and I wondered was whether all of these participants in all periods of the study are actually giving us the same amount of information about the treatment effect. So for example, if we consider those participants who contribute data in this sequence in period 1, are they telling us the same amount, are they giving us the same amount of information as the participants in this highlighted cell of the design? So those participants who provide information in sequence 1 in period 3. Put another way, what cells can we omit with the smallest acceptable decrease in power? So if we were to not take any measurements from this sequence in this period, how much would that inflate how much would that decrease the power we have to detect an effect? And would that be the same as if we didn't include participants in this period in this sequence? So which cells can we omit with the smallest acceptable decrease in statistical power? Or put another way, the smallest acceptable decrease in precision. So all of this is aimed at estimating some treatment effect, and we want to estimate that treatment effect as precisely as we can. So in order to answer this question, we need a statistical model. So I'll show you the actual model in a moment, but before I do, I'll just walk you through the elements of this model. So I'm going to suppose we've got continuous outcomes. So this might be something like the length of stay in a hospital. It could be things like blood pressure, all sorts of continuous outcomes. I'm sure you can imagine many. So we've got our outcome, and we've got this additive model for our outcome. So we've got some period effect. So these stepped wedge trials are being conducted over a duration of time. We've got some confounding of time and treatment. As we progress in the study, more clusters are implementing the treatment. So it's important that we adjust for period in the study, in this model. We've got our treatment effect, and our treatment effect is the whole reason we're doing this trial. This is what we want to estimate. We want to know what the treatment effect is. We've then got our random effects. So these are things that allow us to encode the dependence between our observations from the same cluster. So the period effect and the treatment effect, these are fixed effects. These are things we estimate. Random effects, these are not fixed effects, these are random. These encode this dependence. And then we've got our usual statistical error thrown in as well. So let's take a look at an actual model. So the model that I've written here is quite simple, but models of this form are what are most frequently used in the analysis of continuous outcomes for these sorts of trials. So although this is a simple model, it is a widely used model. So we've got our participant I in period T in cluster K, and that participant's outcome we suppose is equal to some effect of the period that they're measured in. Then we've got our treatment effect theta. So theta is what we are most interested in. This is what we want to estimate. XKT is our treatment indicator. So if cluster K in period T is implementing the intervention, this is equal to 1 and it's 0 otherwise. Then we've got our gamma KT. So our gamma KT is the random effect for our kth cluster in our Tth period. So this is what tells us how correlated the outcomes are for participants in the same cluster. We've got we assume that these gamma Ks, if we consider all of these random effects from the kth cluster across these T periods, then we assume that these are normally distributed with some variance matrix. I'll go into a few examples in a moment. Then we've got our usual random error, normally distributed. All right, so theta is our treatment effect. Theta is what we want to estimate. Theta is why we spend millions of dollars on running one of these studies. Theta hat is the generalized least squares estimator of the treatment effect theta. So this is a standard estimator that we would use to estimate this treatment effect. When we are conducting our sample size calculations or our power calculations, so before we've conducted the study, we need some idea of how variable our estimate is going to be. So we can calculate the variance of theta hat, the variance of this estimator. So this variance is going to depend on this covariance matrix for our random effects, on our variance of our random error, and on the design itself, what the design looks like. So we calculate this variance of theta hat, and this is plugged into our sample size calculations. It's a key ingredient of sample size calculations. So the question we would ask then, how much does this variance increase if observations from a given cell of our design, a cluster period cell of the design, are omitted? What do I mean? Well, we can define the information content of each cell of the design, and that's what I'm going to do now. So the first thing we would do is calculate the variance of the treatment effect estimator for the complete design. So not omitting anything, what is that variance? What's our base level? Then for each of the cells of the design, we would calculate the variance of our treatment effect estimator from the incomplete design, where we omit all of the observations that we would take in that cluster in that period. So we calculate that variance for that incomplete design, and then we define the information content of a cell as the ratio of these two variances. So we've got the variance of our incomplete design, where we omit all of the data from that cluster period cell, and compare that to the variance for the complete design, the full design. So if this is equal to 1, it means that, well, the variance of that incomplete design is equal to the variance of the complete design. So we haven't lost any information by excluding that cell. And if it's greater than 1, then it means we've lost some information. So 1 is our null value for information content. Okay, so I said before that the variance of theta hat depends on the study itself, and it depends upon this variance matrix for our cluster random effects. So I'm going to now give you a bit of an idea of what these variance structures, what these within cluster correlation structures. So the within cluster correlation structure tells us how dependent the observations are from the same cluster. How much dependence do we have there? How does it change? So V gamma is our covariance matrix for our random effects. I'm going to consider the 3 most frequently used structures for this V gamma and think about what these say about the correlations between subjects in the same cluster. So when these subjects are measured in the same or in different periods. So the first model I'm going to consider is the constant correlation or exchangeable model. So this model is still the most widely used in the analysis of and design of these trials. It was first written about back in 2007 by Hussey and Hughes in the first treatment of the theory of stepped wedge designs. So it's often referred to as the Hussey and Hughes model in the stepped wedge literature. So here we've got our usual fixed effects for our outcomes. We've now got our cluster random effects. So we just assume there is some correlation between the observations within a cluster. This doesn't change over time. I will show you in a moment I'll try to give you a bit more insight into what this looks like in a couple of slides. The second model we consider is the block exchangeable model. So this model, we once again have our cluster random effects, but we also include cluster period random effects now. So these are all normally distributed, as is the usual assumption. So what this allows us to do is say that, well, participants who are measured in the same cluster in the same period, they're going to be more highly correlated than if they're in the same cluster but in different periods. Our third model is the discrete time decay model, and this extends that idea. So here we've now got just random effects for our cluster periods, but we assume these have some covariance structure, where the covariance between a pair of observations from the same cluster from the same cluster is going to depend on how far apart in time they're measured. That's what this RTS, r to the power of t minus s, means. I'll now try and give you a bit of an idea of what these correlation structures actually look like. And to do that, I'm going to suppose that we've got cluster K measured over 4 periods with 2 participants in each period. So we've got 8 participants in total. Participants 1 and 2 are in period 1, 3 and 4 are in period 2, and so on. So I'm going to consider 2 ICCs now. The within period ICC. So the within period ICC describes how correlated the outcomes are for participants who are in the same period. So if we consider participants 1 and 2, or participants 3 and 4, 5 and 6, 7 and 8. So what's going on within a period? The between period ICC looks at the correlation between pairs of participants who are in this cluster, but in different periods. So we could look at what's going on when we compare 1 and 3, or 1 and 8, or 3 and 5, for example. So what I'm going to do over the next few slides is consider the correlation between participant 1 and all of these other participants in this cluster. So for the first model, this is what we get. First thing I will note is the correlation of participant 1 with themselves is equal to 1. We then see that with this constant correlation model, this correlation between participant 1 and everyone else is identical. It doesn't change over time. It doesn't matter how far apart in time participant 1 and participant 8, or participant 1 and participant 5 are measured. It just stays constant. Model 2 is this block exchangeable model. And now we're saying that the participants who are measured in the same period are more highly correlated than in different periods. So 1 and 2 have a correlation of row 1, which we expect to be higher than the correlation between 1 and any of the other participants. So that's all equal to row 2 there. So once we move outside of our period, our correlation is going to reduce. But it's not going to decay any further. The discrete time decay model, on the other hand, does allow for this correlation to decay. So here the correlation between 1 and 2 is row, but between 1 and 3, we're now looking at row times r, where r is some decay parameter that's going to be between 0 and 1, indicating how much we expect this to decay. And we can see that we're looking at row times r squared once we move to participants who are in period 3. So 2 periods apart now, row times r to the power of 3 when we're looking at participants who are measured 3 periods apart, period 1 and period 4. So with this discrete time decay model, the correlation between participants decays the further apart in time that they are measured. Okay, so now that we've covered that, we're ready to think again about the information content of these stepped wedge cells in these stepped wedge trials. So I'm going to consider stepped wedge designs, 2 stepped wedge designs, one with 4 periods and another with 10 periods. I'm going to suppose that one cluster has been randomized to each of the sequences of these designs, and that we're measuring 100 participants in each cluster in each period. I'm going to consider two models for the outcome. The first model is this constant correlation model with rho equal to 0.05. The second model is model 3, this discrete time decay model with rho equal to 0.05 and this decay parameter equal to 0.95. Okay, so this is the 4-period stepped wedge design. We've already seen this design today. Here, 0 indicates control, the control condition, 1 indicates the intervention condition. And the 10-period design looks like this. So you can see we've just extended this. We've got a greater number of periods, 10 periods, 9 clusters now. Okay, so let's take a look at the information content of each of the cells for that 4-period design for model 1. This is what we get. And there are some interesting things going on there. Well, the first thing we should do is think about what's being shown here. So here I've color-coded the information content of each of these cluster period cells. So the more red the cell, the greater the amount of information content. I've also popped in the information contents. You can read exactly what the information content is of each of these cluster period cells. So redder means more information. It looks like there are a couple of cells that have an information content of 1. Is this exactly 1, or is it just really close to 1? Are these actually information-free cells that tell us absolutely nothing about the treatment effect? Not sure. We've also got some striking patterns emerging. We can see that in this design, it looks like all 4 corner cells contribute the same amount of information. And then we've got these other pairs of cells which are contributing the same amount of information. Okay, does this pattern persist for our larger design? Well, it looks like it does. We once again have a couple of cells that look like they're contributing absolutely nothing to the treatment effect. All 4 corner cells have the same amount of information. We've got these pairs of cells that are also contributing the same amount of information. A pattern is starting to emerge now. We can see that the cells near the time of the treatment switch are the ones that are contributing a lot of information. But we've also got these hotspots in the corners. Okay, what happens if we start to consider this other model for the outcomes, this discrete time decay model? Okay, so this is what happens for the 4-period design when we consider this discrete time decay model. All right, so things look a little bit different here. We no longer have any cells that are completely, or that appear to be information free. The 4 corners no longer have identical amounts of information, but we still have pairs of cells that are contributing the same amount of information. What happens for the larger design with this same model? Okay, well, we can see that we once again have these pairs of cells that look like they contribute the same amount of information. These ones here, I know that some of them are not exactly equal to 1. It's just we've got a bit of rounding going on here. But some of the other ones are quite close to 1. We've got a pattern emerging again, this band of information richness near the time of the treatment switch. But now it looks like we're getting these kind of smears of information in the first and final periods of the design. Okay, so my colleagues and I, we looked at this and we thought, these are some really interesting patterns. Can we say anything general about these patterns? And after a fair bit of wasted paper, we managed to prove some properties. So it turns out that for models 1, 2, and 3, these correlation structure models, we get this Centro symmetry property. So this means that we do know that pairs of cells, certain pairs of cells, are going to contain the same amount of information about the treatment effect. Further, we know that for models 1 and 2, so the constant correlation model, we get these information-free cells. So there are going to be a couple of cells that tell us absolutely nothing about the treatment effect. So let's just illustrate these two properties using our familiar 4-period design. So the information free property tells us that these two cells are going to contribute absolutely nothing to the estimation of the treatment effect. So we're starting to think, should we even bother taking measurements in those periods? The Centro symmetry property tells us that this pair of cells is going to contain the same amount of information. This pair of cells there, they contain the same amount. This pair, and this pair. So we get some really interesting properties about that point to some very deep symmetrical properties of the stepped wedge design. And I just want to talk a little bit about the symmetry of the stepped wedge for a moment. So the stepped wedge design does possess a particular symmetry. If time were reversed and treatment labels were interchanged, then we'd end up getting the same design. So let's consider the 4-period design. Let's reverse time in this design. So now period 4 is first. Let's interchange our intervention and control labels. And this is starting to look like the original design. Let's just reorder our sequences. There we go. We end up getting the same design that we started with. So this symmetry of the stepped wedge is something that we should be exploiting when we plan these designs, when we consider these designs at all. And a couple of years ago, my colleagues and I, we noticed that some people were proposing new estimators to analyze and plan the stepped wedge design. So new ways of combining information in the stepped wedge design that didn't appear to be exploiting this symmetry of the design. So this work, which was led by Reese, one of the people in our group, showed that optimal estimators for the treatment effect must weight data from cluster period cells in this centrosymmetric fashion. It is a good idea to obey the symmetry of the stepped wedge design when you are analysing it or designing studies, stepped wedge studies. Further, it turns out that if you have an estimator that isn't symmetric, you can really easily symmetrize that estimator and come up with one that is even more efficient, that provides you with greater power to detect the effect that you're interested in. So that was an interesting project that we worked on. Okay, so stepping back then to the information content of the stepped wedge design, of the cells within the stepped wedge design. So let's consider a 15-period design that looks like this and a 20-period design, just to convince ourselves that the properties we observed hold. And I'm going to whiz through this because I see that time is passing. So again, we can see we get this band of information richness, we get information, we get the centrosymmetry property. For this design, we've only got 14 clusters. We don't have any information-free cells here. These ones are not exactly one. The 20-period design, this pattern of information content is becoming really apparent. It looks like we've got this wave of information. There's some sort of wave structure going on here, describing how this information varies. Okay, for the discrete time decay model, we're getting big expanses of very low amounts of information, even more apparent for this larger design. So this work points the way to incomplete designs. It really shows that not all cells in the stepped wedge design are created equal. Do we really need to include those cells with a low information content? So when we conduct these studies, we really want to include the minimum number of participants in order to detect our effect. You want to expose as few people to the risks associated with research as possible. Sometimes those risks will be very minimal. But also collecting data from these participants may be quite expensive. So if we can reduce the amount of measurements we need to take, then we can design trials that cost less money. Okay, so in order to assess this, we considered a real trial that was conducted in Australian rehab units. So this trial was aimed at assessing the impact of an education program in addition to usual care on fall rates in hospital rehab units. So training patients in how to not fall over, essentially. So educating them on the risks of falling and how they could avoid those risks. So the researchers conducted a 5-period 4-sequence step wedge design, 2 rehab units assigned to each of these 4 sequences. So everything I've spoken about up until now has been in terms of equal numbers of participants in each cluster in each period. This design didn't look like that at all. So in this study, we had varying numbers, well, there were varying numbers of participants in each cluster in each period. You can see how this changes over time in each cluster. A lot of differences between clusters as well. So do our theoretical results carry over to this more complicated real-world setting? Well, this is the pattern of information content for this design. So you can see the information content along with the number of participants in each cluster period cell here. So we don't get the exact nice Centro symmetry pattern that we got previously, but we can sort of see that we are getting information richness near the time of the treatment switch. There are some really low information cells that contain a surprisingly high number of participants. So do we really need to recruit participants in each rehab centre in each of these periods? So we could consider all of the million or so possible incomplete designs, but that's a lot of designs to consider. We could do that, it's computationally feasible. But here I'm going to pick a few designs informed by the information content pattern we've seen here and that we've seen for the theoretical setting. So the first design I'll consider looks like this. So this is what I would refer to as a staircase design. Each cluster provides measurements before and after the treatment switch. Design B is the same, but now we include a couple of hotspots. So cells corresponding to the hotspots. Design 3 now has 3 measurement cells per sequence. Design D also does, but now we've offset a couple of those to capture these hotspots. So we've got these 4 designs. I'm going to calculate the variance of the treatment effect estimator for each possible allocation of these 8 clusters to these 4 sequences. So because we've got differing numbers of participants in each cluster period, we consider each possible allocation. There are about 2,500 of those. So if we do that, we can look at the total sample size in each of these 4 designs. So you've got the designs down here. Of course, design A tends to be the smallest design. Design B has a few more. Design C and D aren't too different. They contain the same number of measurement periods. So we wouldn't expect to see too much difference there. That's just because of these varying numbers of participants in each cluster period. Okay, so looking at these sample sizes, we might expect that design C and D are going to turn out to be the most efficient. This is what we end up getting. So here we've got the variances of the treatment effect estimator for each of these possible designs. We want the smallest variance possible. So we can see that design A, that's much higher than anything else. Design C, which contained the greatest number of participants, is not doing the best. Designs B and D are doing the best. And it turns out, well, for my money, design B is your best choice here. It contains the fewest number of measurement periods with really a fairly, compared to these other designs, a fairly competitive variance. So this is the winning design here. And it turns out that this design has 91% power to detect this effect, all of these technical details down here. This is compared to the complete design, which only has 94% power to detect that same effect. So the complete design has just about double the number of measurements as this incomplete design. We are really not losing out much by considering this incomplete design. 91% power is a very competitive level of power for a study to have. So one thing to consider is whether these corner measurements are in fact practical. Does it make sense to go into a cluster, then not visit that cluster for some time before popping back into that cluster to make measurements? I don't know, that depends on subject matter considerations. So it looks like we really are not losing much by considering this incomplete design. So what have we learned about the stepped wedge design? It turns out that periods near the treatment crossover tend to be the most valuable. but these hot corners can add a lot of information. Why are these hot corners popping up in the design? Well, they're necessary to account for time effects. If we accounted for time in a different way, if we perhaps included a linear term for time instead of a categorical term, we would get a different pattern of information content, and these hot corners may not be as important. This pattern of information content also depends on this within cluster correlation structure. It's important to think about the logistical importance versus the statistical value of cells. So as a statistician, I can come up with all sorts of wonderful designs that have fantastic statistical properties. But if I present these to my clinical colleagues, they might take one look at that and tell me it's completely impractical and could never be run in that way. So it's important to balance these statistical considerations with the practical considerations. So a lot of the future work that I'm involved with is on the development of optimal incomplete designs. So how can we use this information content to inform the selection of incomplete designs in a principled way? So this is a question that Ehsan is addressing as the first project in his PhD. Further, we want to investigate these staircase designs, these designs where we only take measurements immediately before and immediately after the treatment switch. It turns out here that that design A, was not an efficient choice. But when is it an efficient choice? Is it ever an efficient choice? Anyway, please, if you have any questions, ask them now, or feel free to get in touch with me at a later date. My email address is there. And if you're after some additional reading, you can read more about our work in these places. Happy to share PDFs with anyone. Thank you.
Well, thanks very much, Jessica. I'll sort of applaud on behalf of everyone here.
Thank you.
As Tom pointed out in the chat, you can ask your questions through Q&A, and what we'll do is we'll allow you to ask the question in person or verbally. And I see one question by Elena. Elena, I'm going to allow you to talk.
Hi, can you hear me?
Yeah.
Yeah.
Okay, great. Thanks for excellent talk. I really enjoyed it. I was thinking about the different time periods, and I was wondering if they all needed to be the same length. And the reason I was thinking about that is because projects that I have, we don't really get to set up the study. It's more like someone gives us data, but maybe if there's been a rollout, it looks like it might be similar data to what you would get for this sort of study. So I wanted to know if the time periods need to be the same, or if, yeah, what it would change if they weren't the same.
No, that is a great question. And I suppose most of the work that has been done does assume that you've got equal length periods, or at least equal numbers of participants in each of your periods. So I suppose more recent work has been focused on the setting where you've got differing numbers of participants in each period of your design. So you would still want, so you can have varying lengths of time. That's fine. And in practice, you know, although we theoretically plan these studies assuming these equal lengths of periods, in practice, when the studies are conducted, things change, things take longer to set up than you think they will, so on and so forth. You may end up with differing period lengths. So you can account for that in your analysis, that's fine. And you can use some of the more recent work that's come out, which allows for differing numbers of participants in each cluster in each period. Mm-hmm. Now, it is important that these periods are aligned across your clusters. It is useful for you to have that. So even if you've got differing length periods, as long as you've got some alignment in time between your clusters, that's fine.
So you'd want like multiple rollouts to multiple participants at the same time, not that everyone's getting their rollout separately, singly.
Yeah, you kind of want everyone to be, all of your clusters are sort of in this amount of time, and we sort of roll things out over that amount of time.
Mm-hmm. Thank you.
I hope that makes sense. Thanks for your question.
Right, thank you. So there's another question by Thermotronica. I'm going to allow you to talk.
Hello?
Hi.
I can hear you.
Oh, okay, thanks.
So what was your question?
Oh, it was if you found an interesting third option that you think would be helpful, or you find interesting, that might make it more three-dimensional.
Oh, okay. So I'm not sure I entirely understand, because I'm not sure I've thought about these designs in the way you seem to be indicating.
Oh, I see. Sorry, go ahead.
No, perhaps you could further clarify, if you don't mind.
Maybe like let's just something like a half dose or a half.
Oh, yeah, okay, yes. I think I understand what you mean. So here we're assuming, in the models I've assumed, we assume that the effective treatment it's like flicking a switch. You're not on any treatment, and then the treatment comes in and treatment is on, it's 100%. But there is often a situation where the intervention that you're considering, it might take some time to ramp up within a cluster. If you're looking at this multifaceted intervention with lots of different components, within clusters, it might take some time for them to implement the entire suite of interventions, for example. So there might be some time where clusters are implementing only, half of the possible things they could be doing, and over time that ramps up. So if you've got this kind of time varying treatment, you can account for that in planning these studies. Certainly the impact that would have on information content is, I think that would be interesting to look at.
Yeah, a three-dimensional model would be fun, with knowing about the that edge correspondence.
And then also, I suppose, thinking about multiple treatments. So if you want to consider, perhaps you've got treatment, you've got your control condition, you've got treatment A, but then in addition, you've got treatment B. You can also, some recent work has been done on stepped wedge designs with multiple different treatments. That's another complexity that is great.
And the hotspots are still the main idea behind them, the step wedge.
Look, I don't know. I think you would still get some. I think it would be interesting to look at that, actually. What happens when you've got multiple treatments? Which treatments which cells are contributing the most to which comparisons? Yeah, that would be interesting.
Yeah, you got it. Thank you very much.
Thank you.
Right, thank you. So I have a question. I'm not a statistician, so this may be very naive. You had some measure of information in your box. Is this about the amount of information or the quality of information, or both?
Yeah, so this is, I guess, the statistical information. So how much does this variance of your treatment effect change if you were to exclude those measurements? So it's not really about the quality as it is about the amount of information, how much is being contributed by the participants in each of those particular cells.
Right. So in the cells where you have little information, then there may be some different type of information.
Well, I think there you might be getting some non-statistical information there. So perhaps information about how the intervention is actually being implemented in a cluster, for example. But you're not getting so much information about your primary outcome, the thing that you're sort of driving towards investigating.
Yeah. Okay. Thanks. Okay, so does anyone else have one final question, perhaps, or yes? It seems not. Okay, well, in that case, I'd like to thank you again, Jess, and everyone for attending and participating in this Matrix online seminar. So enjoy the rest of your day. Bye, everyone. Bye-bye.